And now in this lecture we will find out the radius of the small circle. In the drawing we have this small circle that is inscribed by the semicircle, and we know that line segment CD equals to 3 units in its length, line segment BD equals to 4 units in its length, and the angle CDB, this angle is equal to 90 degrees. It is a right angle, and we want to find out the radius of this small circle. So the first step we'll do construction. We'll complete the semicircle to a circle. So we completed the semicircle to a circle. In the next step we will extend line segment CD by a straight line until it touches the circle. And we'll define the touching point of the extended line segment CD in the circle as point E. So we know that CD is a straight line, and then when we extended the straight line CD by straight line, the result must be a straight line. Therefore, the result that is CE, it also must be a straight line. And we know we have the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on this side of the straight line CE at point D, then in this side of the straight line CE at point D, the sum of the angles must be equal to 180 degrees. So which angles we have at point D at this side of CE? We have here 90 degrees, and we have angle EDB. In total, the sum of those two angles must be equal to 180 degrees, according to the rule that I mentioned, that the sum of the angles on one side of a straight line is equal to 180 degrees. So here we have 90 degrees. This angle is equal to 90 degrees plus this angle that is actually angle EDB. In total, the sum of those two angles must be equal to 180 degrees, according to the rule that I mentioned. Here we will subtract 90 degrees from this equation, and we will get that angle EDB equals to 180 degrees minus 90 degrees, it is 90 degrees. So we actually found out that this angle EDB equals to 90 degrees. Okay. And actually we did a construction from the semicircle. We created a circle. Actually we created another semicircle. This is the second semicircle, and this semicircle is the mirror image of the original semicircle, this semicircle. Okay, again, this semicircle is the mirror image of the original semicircle, of this semicircle. And we know that angle CDB equals to 90 degrees, and angle EDB also equals to 90 degrees. and then we extended the straight line CD by a straight line until it touches the circle as point E. Actually, we created the mirror image of line segment CD. And because of the fact that DE is the mirror image of CD, it means that those two line segments are equal to each other in the end length. That is to say, CD equals to DE, CD equals to DE by symmetry. That is to say, because of the fact that line segment DE is the mirror image of line segment CD, it means that their lengths, the lengths of those two line segments, must be equal to each other, and the only difference between those two line segments is that their directions are in the opposite direction. Exactly like when you look at the mirror, when you see yourself in the mirror, then your dimensions are the same as in the reality, but the direction of your image is the opposite side. Exactly like in the mirror, DE is the mirror image of CD, and because of the fact that DE is the mirror image of CD, it means that their lengths are equal to each other, and the only difference between those two line segments is the direction. Okay? They have here point D that is a common point for those two line segments, and therefore they are in the opposite direction. CD, the direction of CD is upwards, and while the direction of DE is downwards. Anyway, the length of line segment DE equals to the length of line segment DE because of the fact that DE is the mirror image of CD. Okay, so D equals to CD by symmetry. But it is also given us in the question that CD equals to 3 units. So we can write here that CD equals to 3 units. And from this equation, 3 equals to CD equals to DE, we will derive that DE is also equals to 3 units. DE is also equals to 3 units. Okay. In the next step, I will present to you a new rule that is actually rule number 1. Rule number 1 is about two chords that intersect with each other inside the circle. So according to rule number 1, if two chords intersect with each other inside the circle, then the following equation is true. If two chords intersect with each other inside the circle, then the following equation is true. So we actually have this circle, and we have here, inside this circle we have chord AB. This is chord AB. That intersects with chord CD. This is chord CD. I'll repeat again, chord AB intersects with the red chord CD, and the intersection point is at this point. We define the intersection point as point O. So if this is the data that has been given to us, that is to say, if chord AB intersects with chord CD at point O, then the following equation is true, that AO times OB equals to CO times OD. I'll repeat again. If chord AB intersects with chord CD at point O is the intersection point between chord AB and chord CD that is happening inside this circle, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. Okay? So we actually can implement rule number 1 in our drawing, because in our drawing we have chord AB. This chord AB intersects with chord CE at point D. I'll write it down. In our drawing, we have chord AB intersects with chord CE at point D. At point D. Point D is the intersection point of chord AB with chord CD. I'll repeat again. Chord AB intersects with chord CE at point D. Point D is the intersection point of chord AB with chord CE. Again, point D is the intersection point of chord AB with chord CE. Therefore, according to rule number 1, we get that AD times DB equals to CD times DE again. AD times DB equals to CD times DE. Okay, write it down. AD times DB equals to CD times DE. I repeat again. According to rule number 1, we get that in our specific drawing we have AD times DB must be equal to CD times DE. Again, AD times DB equals to CD times DE. Okay. ED is the missing line segment, so we will leave it as it is. Times dB. We know that dB equals to 4 units according to what is given us in the question. So we substitute dB by 4. And it is equal to CD, that is 3 units, times DE, that is also 3 units. So in conclusion, we found out that AD times 4 equals to 3 times 3. So that is to say 4AD equals to 3 times 3, that is 9. Okay. Here we divide this equation by 4, and we get that the missing line segment AD is equal actually to 9 over 4 units. AD equals to 9 over 4 units. So here we found out that AD equals to 9 over 4 units. Actually, we know that AB is the diameter of the semicircle and also the diameter of the circle itself. Okay? And the diameter of any circle or semicircle is twice as long as the radius. So, if we divide the diameter AB by 2, we get the radius of the circle, of the big circle, that is also the radius of the semicircle. We define the radius of the big circle as capital R, and we get that capital R equals to AB over 2. Okay? And what is the value of the diameter AB? AB equals to AD plus DB again. AB equals to AD plus DB. And if we divide it by 2, we get the radius that is equal to capital R. The radius of the big circle equals to capital R. So here we have already found out that AD equals to 9 over 4. And dB equals to 4 units according to what is given us in the question. Again, dB equals to 4 according to what is given us in the question, all divided by 2. So here we'll multiply 4 by 4 and then we'll divide it by 4 in order to have a common factor of 9 over 4. And we'll get it 9 over 4 plus 16 over 2, that is equal to 9 plus 16, that is 25, over 4, and we remove 2 to the denominator, so it will be 4 times 2. In conclusion, we found out that the radius of the big circle that is equal to capital R, it is equal to 25 over 4 times 2 is 8. So the radius of the big circle, this is also the radius of the semicircle, equals to 25 over 8 units. Okay. In the next step, we will define the center of this big circle as point P. Here, point P is the center of the big circle. And we'll define the center of the small circle. This point is point Q. And we'll define the center of the small circle is point Q. It's Q. And here, from point Q, we know that the point of tendency of tangent CD with this small circle, we define it as point O. And we'll define the point of tendency of tangent DB, this tangent DB with this small circle, is point M. So in the next step, we will join together points Q and O by straight line. And we will actually define the radius of the small circle as small r. Therefore, QO will be the radius of the small circle. Why? Because point Q starts from the center of the circle and ends at point O, that is the point on the small circle itself. Therefore, QO is the radius of the small circle that is equal to R. Likewise, we join points Q and M together by straight line. So here, QM is also the radius of the small circle, that is to say it is equal to R. Because of the fact that line segment QM starts from point Q, that is the center of the small circle, and point M is the point on the small circle itself, QM is defined as the radius of the small circle that is equal to small r. So here we have the radius QM that is drawn to the point of tendency, that is to say the radius QM is drawn to point M, that is the point of tendency of tangent DB with this small circle, and whenever you have a radius that is drawn to the point of tendency, then this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Okay? And here we have the radius QO. QO is the radius of the small circle that is equal to small r. The radius QO, it is drawn to the point of tendency, that is to say, it is drawn to point O, that is the point of tendency of tangent CD with those small circle. And whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, CD is perpendicular to BQ. So if CD is perpendicular to BQ, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Okay? In the next step, we will focus on quadrilateral OQDM. In quadrilateral OQDM, we have 1, 2, 3 right right angles. So the sum of three right angles is 90 times 3 is 270 degrees. So the sum of three right angles in quadrilateral OQDM is 270 degrees, plus the size of the fourth angle that is actually angle OQM. In total, the sum of those four angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Okay? So here we'll subtract 270 degrees from this equation, and we'll get that angle OQM equals to 360 degrees minus 270 degrees, it is 90 degrees. So we found out that the missing angle OQM is the right angle, it is equal to 90 degrees. Okay, so this angle equals to 90 degrees. So actually, quadrilateral OQDM has four right angles. And we know that any quadrilateral that has four right angles must be at least a rectangle. So we will relate to quadrilateral OQDM as a rectangle. I write it down. Quadrilateral OQDM is a rectangle because of the fact that it has four right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say, OQ equals to DM. OQ equals to DM. Okay. But we know that OQ equals to R, it is the radius of the small circle. You can write here that OQ equals to small r, and from this equation small r equals to OQ equals to dm, we derive that dm is also equals to r. dm is also equals to r. So we found out that dm equals to r, it is the radius of the small circle. Okay, dm equals to r. So I tell that dm equals to r. Okay. We found out that dm equals to r. It is the radius of the small circle. And what is the length of line segment dp? The length of the small line segment dp From the drawing, it is very easy to see that the length of small line segment DP is equals to dB minus PB. dB minus PB. Again, the length of the small line segment DP equals to dB minus PB. dB equals to 4 units, it is given us in the question. Minus PB. What is PB? P is the center of the big circle. B is a point on the big circle itself. Therefore, PB is the radius of the big circle. So, if PB is the radius of the big circle, it means that it is equal to capital R. Okay? So, in conclusion, we found out that dP equals to 4 minus R, but we already found out that R equals to 25 over 8, so we substitute R by 25 over 8. So dP will be equal to 4 minus 25 dP equals to 4 minus 25 over 8. Here we multiply 4 by 8 and then we divide it by 8 in order to overcome a factor which is 25 over 8. And we get that dP equals to 8 times 2 is 32. Again, we know that dP equals to 4 minus 25 over 8. So we multiply 4 by 8 and then we divide it by 8 in order to overcome a factor of 25 over 8. And we get that dP equals to 4 times 8 is 32 minus 25 over 8. 32 minus 25 is 7, so I say 7 eighths. Okay, so dP equals to 7 eighths. So we can write here that dP equals to 7 eighths. Again, dP equals to 7 eighths. Okay. And what is the value of PM? From the drawing, it is very easy to see that PM equals to dm minus PD. PM equals to dm minus dP. Okay? Here, PM equals to dm minus dP. So PM equals to dm equals to R, according to what we have already found out, dm equals to R. We substitute dm by small r, and dP equals to 7 eighths. I repeat again. In conclusion, we found out that PM equals to small r minus 7/8. In the next step, I will present to you a new rule that is actually rule number 2. But first of all, we will define the touching point of the small circle with the big circle. This point is point S. Point S is also called the launch point. The launch point between the two circles, but you can call it also the point of contact or the point of tendency. So here we have the big circle is tangent to the small circle at point S, and the small circle is located inside the big circle, and those two circles, they touch each other. They have the internal launch at this point. That is to say, those two circles touch each other internally at this point. So this type of tendency is defined as an internal launch. Why? Because the small circle is located inside the big circle. Okay? So in the next step I will present to you new rule number 2. According to rule number 2, if two circles have an internal launch between them, two circles have an internal launch between them, then the straight line that connects their centers if two circles have an internal launch between them, then the straight line that connects their centers passes through the launch point of the two circles. So the definition of point S is a launch point, or you can call it also the point of tendency, also the touching point between the two circles. So I read rule number 2 again. According to rule number 2, if two circles have an internal notch between them, then the straight line that connects the centers of their then the straight line that connects their centers passes through the launch point of the two circles. So here, what is the meaning of rule number 2? The meaning of rule number 2, that if we know that those two circles, we know that they touch each other internally, it's point S. Point S is the launch point between those two circles, the small circle and the big circle. Then, according to rule number 2, the straight line that connects the two centers together, that is to say, point P is the center of the big circle, point Q is the center of the small circle, and the straight line that connects the two centers together is line segment PQ. And according to rule number 2, this line segment PQ passes through point S, that is the launch point of the two circles. That is to say, points P, Q, and S are located on the same straight line, or PQS is one straight line. Okay, you can conclude from rule number 2 that line segment PQS is one straight line. One straight line, that is to say, all the 3 points P, Q, and S are located on the same straight line. Okay? Or PQS is a straight line. According to rule number 2, of course. So, what is the definition of line segment QS? Q is the center of the small circle. S is the point on the circle itself. Again, Q is the center of the small circle. S is the point of the small circle itself. This is exactly the definition of a radius. That is to say, QS is the radius of the small circle that is equal to small r according to our definition. Okay? And what is the definition of line segment PS? P is the center of the big circle. S is the point on the big circle itself. That is to say, PS is the radius of the big circle that is equal to capital R. So PS equals to capital R, but we already found out that capital R equals to 25 over 8. That is to say, PS equals to the radius of the big circle that is equal to 25 over 8 units. Okay? And here we have already found out that PM equals to R minus 7/8. So I write it down. QM equals to R. And what is the length of line segment PQ? Here, PQ from the drawing it is very easy to see that the length of line segment PQ is equals to, PQ equals to PS minus SQ. Again, from the drawing, it is very easy to see that PQ equals to PS minus SQ. Okay? So PQ equals to PS. We already found out that PS is equal to the radius of the big circle. This is to say it is equal to capital R minus SQ. We already found out that SQ equals to small r. So in conclusion, we found out that PQ equals to capital R minus R. But we already found out that capital R equals to 25 over 8, so we can substitute capital R by 25 over 8, and we get that PQ, the length of line segment PQ, it is equal actually 25 to 25 over 8 minus small r. Okay? PQ equals to 25 over 8 minus small r. So we can write here that PQ, this line segment, is equal to 25 over 8 minus r. Okay. Now I will copy the right triangle QPM in a new page. I will copy the green right triangle QPM in a new page, and we will implement the Pythagoras theorem on the right green triangle QPM. The only missing variable here in the right triangle QPM is small r, and small r is the variable that we are looking for in this lecture. We want to find out the radius of the small circle that is equal to small r. By implementing the Pythagoras theorem on the green right triangle QPM, we will find out the value of small r, that is the radius of the small circle, that is the radius that we are looking for. So we copy the right triangle PQM in a new page, and we implement the Pythagoras theorem on the right green triangle PQM. So this is the right triangle QPM that I copied from the original drawing. We have already found out that the hypotenuse QP equals to 25 over 8 minus small r. We have already found out that PM equals to small r minus 7/8. And we have already found out that QM equals to small r, that is the radius of the small circle. Okay? So this is the right triangle QPM. And we will implement the Pythagoras theorem in this right triangle. So by PT is the abbreviation for Pythagoras theorem. Okay, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here, in this right angle QPM, the hypotenuse is PQ, therefore the square of the hypotenuse is PQ squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to QM squared plus PM squared. Okay? So here, PQ equals to 25 over 8 minus small r. Therefore, PQ squared is 25 over 8 minus r squared. That is equal to QM squared. QM is r, so QM squared is r squared or small r squared plus PM. PM is r minus 7/8. Therefore, PM squared will be equal to r minus 7/8 squared. Here we will open the brackets on both sides of this equation, equation number 1, and we get that according to equation number 1, 25/8 minus r squared is equals to 25 over 8 squared, that is 25 squared, that is 625, over 8 squared, that is 64, plus r squared, minus 2 times 25 over 8 times r. In the other side of the equation we have r squared plus 7/8 squared. So we have r squared plus 7/8 squared is 49 over 64 minus 2 times r times 7/8. Okay? So here we have r squared on both sides of the equation, so r squared will get cancelled. After we cancel r squared, in this side of the equation, we left only with 625 over 64 minus, here we have 2 times 25r over 8. So we divide both the numerator and the denominator of this expression by 2. 2 over 2 is 1, so 2 will get cancelled. In the numerator we left only with minus 25 small r. In the denominator we have 8. We must divide 8 by 2 because we divided both the numerator and the denominator by 2. 8 over 2 is 4. So in conclusion, this expression equals to minus 25 small r over 4, and it is equal to r squared plus 49 over 64. Here this expression minus 2r times 7 over 8. We divide both the numerator and the denominator by 2. So here we get that minus 2 over 2 is minus 1, so minus 2 will get cancelled, and in the numerator we left only with minus 7r over 8. We divide 8 by 2 and we get 4. So in conclusion, this expression equals to minus 7r over 4. Okay, in the next step we will multiply this equation, equation number 1 by 64, and we get that according to equation number 1, here we have 64 over 64 is 1, so we left only with 625. minus, here we multiply this expression by 64, so it will be minus 64 over 4, that is minus 16. And we're left with 25R. So in conclusion, this expression equals to minus 16 times 25R. That is equal to, here we multiply this equation number 1 by 64. So R squared times 64 is 64R squared. Here we have 64 over 64 is 1, so we left only with 49 here. This expression equals to 49. And here we have, we multiply this expression 17R over 4 by 64. So here we will have minus 64 over 4 is minus 16. And we have also to multiply it by 7R. So in conclusion, this expression minus 7R over 4, after we multiply it by 64, it is equal to minus 16 times 7 small r. Okay? So here, turning to equation number 1, we found out that 625, here minus 16 times 25R is minus 400R. That is equal to 64R squared plus 49. Here we have minus 16 times 7R is minus 112R. Okay, so here we will add 400R to this equation number 1. We'll add 400R and we get that here we have 625. 400R minus 400R is 0. So we left in this side of the equation only with 625, that is equal to 64R squared plus 49, and 400R minus 112R, it is equal to plus 288R. Here we will subtract 625 from this equation number 1, and we get that according to equation number 1, 625 minus 625 is 0. So in this side of the equation we have 0. That is equal to 64R squared plus 288R. And here we have 49 minus 625. It is equal to minus 576. In conclusion, we found out that 0 equals to 64R squared plus 288R minus 576. Here we will divide this equation number 1 by 32, and we get that according to equation number 1, 64 over 32 is 2, so this expression equals in total to 2R squared plus 288 over 32 equals to 9R. Here minus 576 over 32 equals to minus 18, and 0 over 32 is 0. So in conclusion, found out that according to equation number 1, we have the quadratic equation that 2r squared plus 9r minus 18 equals to 0. In this quadratic equation, the coefficient a equals to 2. The coefficient b equals to 9 and the coefficient c equals to minus 18. And the variable that we are looking for in this quadratic equation, equation number 1, is r. So x equals to r. And the general formula for solving out the quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. So here the variable that we are looking for in our specific quadratic equation is a, so x is r. The variable that we are looking for in this quadratic equation is small r, that is the radius of the small circle. So therefore x equals to r. We will substitute x by small r. R equals to minus b, b equals to 9. So minus b equals to minus 9 plus minus square root of b squared. B equals to 9, so b squared is 9 squared, that is 81. Minus 4 times a is 2, times c is minus 18. All divided by 2 times a is 2, so 2 times 2 is 4. So here we will get that r equals to minus 9 plus minus the square root of 81, and here we have minus 18 minus 2 is minus 36, and minus 36 times minus 4 is plus 144. All divided by 4. Okay, so actually r, the radius of the small circle, small r, it is equal to minus 9 plus minus the square root of 81 plus 144 is 225. So inside the root we left only with 225, all divided by 4. So here r, the radius of the small circle, is equals to minus 9 plus minus the square root of 225 is 15, all divided by 4. So here we have two solutions that are possible for r. The first solution for r is that r, the radius of the small circle, equals to minus 9 minus 15 over 4. Minus 9 minus 15 is minus 24, and minus 24 over 4 is minus 6. So we found out that r equals to minus 6, that is a negative number. But here r is the radius, the length of the radius of this small circle. So r is a length, r is a length, and as a length, it must be a positive number. Therefore, r can never be equal to minus 6, that is a negative number. So we left only, we cancel this solution, and we left only with the second solution, that r equals to minus 9 plus 15 over 4. Minus 9 plus 15 is 6 over 4. Here we'll divide both the numerator and the denominator of 6 over 4 by 2. 6 over 2 is 3 and 4 over 2 is 2. So conclusion found out that R, the radius of the small circle, equals to either 3 halves, or in terms of numbers it is equal to 1.5 units. Okay. I'll repeat again. We found out that the radius of this small circle, it is equal to either 3 halves, or in terms of numbers it is equal to 1.5 units. We finished to answer this question. In the next step, we will summarize the lecture. Actually, we wanted to find out the radius of this small circle. We have here a semicircle, and inside this semicircle we have this small circle. So this small circle is inscribed by the semicircle. And we also know that 9 segment CD equals to 3 units, 9 segment DB equals to 4 units, and angle CDB equals to 90 degrees, and then we want to find out the radius of this small circle that is inside the semicircle. It's located inside the semicircle. So in order to find out the radius of this small circle, we made a construction. We extended this semicircle to a circle, and then we extended 9 segment CD by a straight line until it touches the circle at point E. Point E is the touching point of the extended 9 segment CD and this circle. So here, by completing the semicircle to a circle, we created another semicircle. This is the second semicircle. This second semicircle is a mirror image of the original semicircle. Okay, so this semicircle is a mirror image of this semicircle. Okay, and then we actually extended the straight line CD by straight line, and we got 9 segment CE. And if you extend a straight line by straight line, the result must be a straight line. So CE must be a straight line. And we know that the sum of the angles on one side of a straight line is equal to 180 degrees. So if you focus on this side of the straight line CE, at point D, then the sum of the angles at point D, at this side of CE, it must be equal to 180 degrees. So which angles we have at point D? We have here 90 degrees, and then get EDV. In total, the sum of those two angles must be equal to 180 degrees according to the rules that I mentioned. So here 90 degrees plus angle EDV must be equal to 180 degrees. We subtracted 90 degrees from this equation and we found out that the missing angle EDV, this angle EDV equals to 90 degrees. Okay? So actually, I've already mentioned that the lower semicircle is the mirror image of the upper semicircle. And this angle equals to 90 degrees. Angle CDB equals to 90 degrees, and angle EDB also equals to 90 degrees. For that reason, DE, line segment DE, is also the mirror image of line segment CD. Okay? Because of the fact that DE is the mirror image of CD, it means that both line segments are equal to each other in their lengths. Okay, here CD equals to DE because of the fact that DE is the mirror image of CD. Okay, and whenever you look at yourself in a mirror, then you see yourself exactly in the same dimensions as you are in reality, but in the opposite side. Okay? And also, the same thing is true to say about CD and DE. DE is the mirror image of CD, therefore the length of CD must be equal to the length of DE, and the only difference between those two line segments is their direction. Here they have the common point D, and while DC goes to the upper direction, DE goes to the lower direction. But their lengths are equal to each other, exactly as a mirror image. So CD equals to DE because of the fact that DE is the mirror image of CD, and when you have mirror image and the image, the length of the mirror image must be equal to the length of the image itself. So here DE, that is the mirror image of CD, must be equal to CD. That is to say, DE equals to CD by symmetry, because DE is the mirror image of CD. Okay, but it is given as the question that CD equals to 3 units. So we can write here that CD equals to 3 units, and from this equation 3 equals to CD equals to DE, we will derive that DE is also equals to 3 units. Here, DE, line segment DE equals to 3 units. Okay? In the next step, I presented to you rule number 1. According to rule number 1, if two chords intersect with each other inside the circle, then the following equation is true, that AO times OB equals to CO times OD. So here we have this circle, and inside this circle we have chord AB that intersects with chord CD at point O. Point O is the intersection point of chord AB with chord CD. Therefore, if this is the data that has been given to us, then according to rule number 1, we will get that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. Okay? So we actually can implement rule number 1 in our drawing. Why? Because in our drawing, we have chord AB that intersects with chord CE at point D. Point D is the intersection point of chord AB with chord CE. I repeat again. Chord AB intersects with chord CE at point D. Point D is the intersection point of chord AD with chord AB with chord CE. Therefore, according to rule number 1, we'll get that AD times DB equals to CD times DE. Again, AD times DB equals to CD times DE. According to rule number 1, AD times DB equals to CD times DE. Okay, AD is the missing line segment. DB equals to 4 units according to what is given as the question. We have already found CD equals to 3 units according to what is given us in the question. That we found out that DE equals to 3 units also. It is the mirror image of CD. So in conclusion, we found out that according to rule number 1, AD times 4 equals to 3 times 3. 3 times 3 is 9. So 4 times AD equals to 9. We divided this equation by 4 and found out that AD equals to 9 over 4. Here AD equals to 9 over 4. So now we know that AB is the diameter of the circle, of the big circle, and also the diameter of the semicircles. And the diameter is twice as long as the radius. So if we divide the diameter AB to 2, we will get the radius of the big circle. So we'll define the radius of the big circle as capital R. And therefore we get that capital R equals to the diameter AB over 2. The diameter AB equals to AD plus DB. And if we divide this by 2, we'll get the radius that is equal to capital R. We already found out that AD equals to 9 over 4, DB equals to 4 units, it is given as the question, and if we divide it by 2, we'll get the radius of the big circle. So here we multiplied 4 by 4, and then we divide it by 4 in order to have a common factor with 9 over 4. And we got that 9 plus 4 times 4 is 16, over 4 over 2. 9 plus 16 is 25. And then we moved 2 to the denominator, and we got that R, capital R equals to 25 over 4 times 2. 4 times 2 is 8, so in conclusion we found out that the radius of the big circle that is equal to capital R, it is equal to 25 over 8 units. The radius of this big circle, that is also the radius of the semicircles, it is equal to 25 over 8 units. Okay? Then we defined the center of this big circle as point P, and we defined the center of this small circle as point Q. And then from point Q, that is the center of the small circle, we define the radius of the small circle as small r, and from point Q, that is the center of the small circle, we drew the radius to the point of tendency to point O. Point O is the point of tendency of tangent CD with this small circle. So we drew the radius QO to the point of tendency, and whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. That is to say, in this case, CD will be perpendicular to the radius OQ. If CD is perpendicular to OQ, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Okay? Likewise, from point Q, we drew the radius QM that is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent DB with this small circle. And whenever we have a radius that is drawn to the point of tendency, then the tangent DB will be perpendicular to the radius MQ. So if DB is perpendicular to MQ, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. So actually, in quadrilateral OQDM, we have 1, 2, 3 right angles. Okay, I'll repeat again. In quadrilateral OQDM, we have 3 right angles. The sum of right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle of quadrilateral OQDM. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. We subtracted 270 degrees from this equation, and we found out that the missing angle AMOQ equals to 360 degrees minus 270 degrees, it is 90 degrees. So we found out that this missing angle OQM equals to 90 degrees. Therefore, actually in quadrilateral OQMD, we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle. So we will relate to quadrilateral OQDM as a rectangle. Okay? And we know that the opposite sides of a rectangle are equal to each other. So in rectangle OQDM, its opposite sides, they are equal to each other. That is to say, OQ equals to DM. OQ equals to DM, according to the rule that the opposite sides of a rectangle are equal to each other. But OQ equals to R, according to what we already found out, OQ equals to R, some small r. That is the radius of the small circle. And from this equation, R equals to OQ equals to dm, we derive that dm is also equals to r. Here, dm equals to r. Okay? And what is the value of the length of the small line segment dp? From the drawing, it is very easy to see that dp equals to db minus pb. Again, dp equals to db minus pb. db equals to 4 units according to what is given as the question. What is pb? P is the center of the big circle. B is the point on the big circle itself. This is exactly the definition of a radius. That is to say, PB is the radius of the big circle that is equal to capital R. In conclusion, DP equals to 4 minus capital R. But we have already found out that capital R equals to 25 over 8, so we can substitute capital R by 25 over 8. We did it, and we got that DP, the small line segment DP, equals to 4 minus 25 over 8 in its length. So here we multiplied 4 by 8 and then we divided by 8 in order to have a common factor with 25 over 8. 4 times 8 is 32, so in the numerator we have 42 minus 25, that is 7, and in the denominator we have 8. So in conclusion we found out that DP, the length of the small line segment DP, is equal to 7/8. DP equals to 7/8. So we wrote here that DP equals to 7/8. Then found out the length of line segment PM. From the drawing it is very easy to see that PM equals to DM minus DP. PM equals to DM minus DP. So DM equals to R, which is the radius of the small circle. We substituted DM by R. DP, we already found out that DP equals to 7/8. So in conclusion, we found out that PM equals to capital R minus 7/8. Okay, PM equals to capital R minus 7/8. Then I presented to you rule number 2. According to rule number 2, if two circles have an internal length between them, then the straight line that connects their centers passes through the launch point of the two circles. So what is the meaning of rule number 1? The meaning of rule number 1 is that if we have two circles that have an internal length between them, like in this drawing, this small circle have an internal length with this big circle. That is to say, those two circles, they are touching each other internally at point S. It is defined as internally because of the fact that the small circle is located inside the big circle. So those two circles have an internal length between them at point S. Point S is the launch point or the point of tendency or point of contact or the touching point of those two circles. And according to rule number 2, the straight line that connects between the centers of those two circles, here, Q is the center of the small circle, P is the center of the big circle. And the straight line that connects between their centers is the straight line PQ. This straight line PQ, according to rule number 2, passes through the launch point of the two circles. That is to say, PQ passes through point S, that is the launch point of those two circles, or between those two circles. Again, the straight line PQ that connects the two centers P and Q, actually PQ is a straight line that connects the two centers together, and this straight line passes through point S, that is the launch point of those two circles. That is to say, according to rule number 2, P, Q, and S, those 3 points are all located on the same straight line. Again, point Q, and point S, all those 3 points are, all of them are located on the same straight line. Or that is to say, PQS is one straight line. Okay? Here, PQS is one straight line according to rule number 2. Okay? And what is the length of line segment QS? Q is the center of the small circle. S is the point of the small circle itself. This is exactly the definition of a radius. That is to say, QS is the radius of the small circle that is equal to small r. And what is the definition of line segment PS? P is the center of the big circle. S is the point of the big circle itself. This is exactly the definition of a radius. That is to say PS equals to capital R, that is the radius of the big circle. But we have already found out that capital R equals to 25 over 8. That is to say PS equals to 25 over 8. And what is the length of PQ? From the drawing it is very easy to see that PQ equals to PS minus QS. Again, PS minus QS equals to PQ. I'll repeat again. PQ equals to PS minus QS. We have already found out that PS equals to capital R. So we substitute PS by capital R. And QS, we have already found out that QS equals to small r. In conclusion, we found out that PQ equals to capital R minus small r. But we have already found out that capital R equals to 25 over 8. So we can substitute capital R by 25 over 8. We did it, and we got that the length of line segment PQ equals to 25 over 8 minus r, minus small r. Okay? So we know that PQ equals to 25 over 8 minus small r. We want to find out that PM equals to small r minus 7/8 and QM equals to small r. That is to say, we have all the sides of the green right triangle, triangle QPM. Therefore, if we implement the Pythagoras theorem on this right small triangle, right green small triangle, we will find out the only missing variable is that is small r, the radius of the small circle. So I copy the right triangle QPM in this new page. We already found out that QP equals to 25 over 8 minus r, PM equals to r minus 7/8, and QM equals to small r. Now we will implement the Pythagoras theorem on this right triangle in order to find out the value of small r, that is the radius of the small circle that we are looking for. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is PQ and the square of the hypotenuse is PQ squared. It is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to QM squared plus PM squared. PQ equals to 25 over 8 minus r. Therefore, PQ squared equals to 25 over 8 minus r squared. That is equals to QM squared. QM equals to r, so QM squared is r squared plus PM squared. PM equals to r minus 7/8. So PM squared is r minus 7/8 squared. Here we open the brackets on both sides of equation number 1 and found out that 25h minus r squared equals to 25 over 8 squared. 25 squared is 625 over 8 squared is 64 plus r squared minus 2 times 25 times r. According to the algebraic identity, that a plus a minus b squared equals to a squared plus b squared minus 2 times ab. So here we have r squared, and we open the brackets here in r minus 7/8 squared. It is equal to r squared minus 7/8 squared. 7/8 squared is 7 squared, that is 49 over 8 squared, that is 64. Okay, in conclusion, 7/8 squared equals to 49 over 64 minus 2 times r times 7/8. Okay, so here we have r squared on both sides of the equation, so r squared will get cancelled. And here we have 625 over 64. Here we have 2 times 25r over 8. Minus 2 times 25r over 8. We divided both the numerator and the denominator by 2. Minus 2 over 2 is minus 1, so 2 will get cancelled. So in the denominator we left only with minus 25r. In the denominator we have 8 over 2, that is 4. So in conclusion, this expression, minus 2 times 25r over 8 equals to minus 25r over 4. And it is equal to r squared plus 49 over 64 minus 2r times 7 over 8. We divided both the numerator and the denominator by 2. Minus 2 over 2 is minus 1, so minus 2 will get cancelled. And in the denominator we left only with minus 7r. In the numerator we left only with minus 7r, and in the denominator we have 8, so we have to divide 8 by 2. 8 over 2 is 4, so in conclusion this expression equals to minus 7r over 4. We multiplied this equation number 1 by 64, and found out that here 625 times 64 over 64. 64 over 64 is 1, so we left only with 625. Here we have minus 25r over 4 times 64. So it is actually minus 64 over 4, that is minus 16. So in conclusion, this expression equals to minus 16 times 25r. In the other side of the equation we have r squared times 64 is 64r squared, and we have 49 times 64 over 64 equals to 49, and we have here minus 7r over 4 times 64. It is actually minus 64 over 4, that is minus 16. So this expression equals to minus 16 times 7r. Okay, so this is the expression that we got from equation number 1. And here we have 625 minus 16 times 25r equals to minus 400r. We have 64r squared plus 49 minus 16 times 7r equals to minus 112r. Here we added 400r to this equation number 1, and we got that 625 400r minus 400r is 0, so we left only with 625 in this side of the equation number 1. In the other side of the equation number 1 we have 64r squared plus 49, and 400r minus 112r equals to 288r. Okay, here we subtracted 625 from this equation number 1, and we got that 625 minus 625 is 0. We have here 64r squared, and we have also plus 288, and we have 49 minus 625 equals to minus 576. So in conclusion, according to equation number 1, we got that 0 equals to 64r squared plus 288r minus 576. We divided this equation number 1 by 32, and we got that according to equation number 1, 2r squared, 64 over 2 is 64 over 32 is 2, so this expression equals in total to 2r squared. 288r over 32 equals to 9r, and minus 576 over 32 equals to minus 18r. So in conclusion, we got the quadratic equation that 2r squared plus 9r minus 18 equals to 0. In this quadratic equation, the coefficient a equals to 2, the coefficient b equals to 9, the coefficient c equals to minus 18, and the variable that we are looking for in this quadratic equation is small r. So x equals to r. And the general formula for solving out a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, the variable that we are looking for is r, small r, so we substitute x by small r. So small r equals to minus b equals to 9, so minus b is minus 9, plus minus b squared. B equals to 9, so b squared is 9 squared, that is 81. Minus 4 times a is 2, times c is minus 18. Okay, so r equals to minus 9 plus minus, we have 81, minus 4 times 2 is minus 8, and minus 8 times minus 18 is plus 144. So In conclusion, found out that inside the root we have 81 plus 144. So r equals to minus 9 plus minus 81 plus 144 over 4. 144 plus 81 equals to 225. So inside the root we left only with 225. So r equals to minus 9 plus minus square root of 225 over 4. The square root of 225 is 15. So here we will have two solutions that are possible for r. The first solution for r is that r equals to minus 9 minus 15 over 4. Minus 9 minus 15 is minus 24. It's minus 24 over 4 is minus 6. So we found out that r equals to minus 6, that is a negative number, but because of the fact that r is the length of the radius of the small circle, r is a length, it must be a positive number. So r can never be equal to minus 6, that is a negative number. So we cancel the solution, and we left only with the second solution, that r equals to minus 2 plus 15 over 4. Minus 2 plus 15 is 6, so we have 6 over 4. We divided both the numerator and the denominator of this 6 over 4 by 2. 6 over 2 is 3 and 4 over 2 is 2. So in conclusion, we found out that r, the radius of the small circle, it is equal this, the radius of this small circle r, it is small r equals to either 3 halves, it is equal to either 3 halves, or in terms of numbers, it is equal to 1.5 units. I'll repeat again, r, the radius of this small circle, it is equal to either 3 halves, or in terms of numbers, it is equal to 1.5 units. Okay, thank you very much.